nuclear weapons stand as a stark symbol of humanity's capacity for both innovation and destruction. Their power, derived from the very heart of matter, represents a force unlike any other witnessed on Earth. These weapons, capable of obliterating entire cities in a blinding flash, have cast a long shadow over international relations and the fate of humankind since their inception. Understanding the science behind these devastating devices is crucial to grasping the profound implications they hold for our world. The story of nuclear weapons is a complex tapestry woven from scientific breakthroughs, political machinations, and moral dilemmas. It is a story that compels us to confront the duality of our nature, our ability to unlock the secrets of the universe, and our potential to wield that knowledge for unimaginable destruction. In the exploration of this formidable force, we are forced to grapple with the very essence of existence and the precarious balance between progress and annihilation. The journey that culminated in the creation of nuclear weapons began in the realm of theoretical physics. In the early 20th century, scientists were beginning to unlock the secrets of the atom, discovering a universe of particles and forces within its infinitesimal boundaries. The groundbreaking work of Albert Einstein, particularly his famous equation E+mc2, laid the foundation for understanding the immense energy locked within the atom's core. The discovery of nuclear fission in the late 1930s, a process by which the atom's nucleus could be split, releasing tremendous energy, marked a pivotal moment in this journey. The potential for harnessing this power for both peaceful and destructive purposes became readily apparent, and the race to develop nuclear weapons began in earnest. World War II provided the grim backdrop for the culmination of this scientific endeavor. Driven by the fear that Nazi Germany might develop nuclear weapons first, the United States embarked on the Manhattan Project, a top-secret research and development undertaking that brought together some of the world's most brilliant minds. In 1945, the project bore its terrifying fruit with the creation of the first atomic bombs. The world watched in horror as these weapons were unleashed upon the Japanese cities of Hiroshima and Nagasaki, marking the dawn of the nuclear age. The devastation wrought by these bombs, the sheer scale of death and destruction, sent shockwaves across the globe, forever altering the course of human history. Nuclear weapons derived their power from the processes of nuclear fission and nuclear fusion. Fission bombs, the type used in the attacks on Hiroshima and Nagasaki, work by splitting the nuclei of heavy atoms, such as uranium or plutonium. This splitting, triggered by a neutron, releases a tremendous amount of energy and more neutrons, setting off a chain reaction that propagates through the fissile material. Fusion bombs, also known as hydrogen bombs or thermonuclear weapons, harness the power of nuclear fusion, the process that powers the sun. These weapons fuse together light atomic nuclei, such as isotopes of hydrogen, deuterium, and tritium, under immense heat and pressure. The resulting fusion reaction releases even greater amounts of energy than fission reactions, creating explosions of unparalleled power. The construction of a nuclear weapon involves a complex interplay of physics, engineering, and materials science. The core of a fission bomb consists of a critical mass of highly enriched uranium or plutonium, carefully shaped and arranged to optimize the chain reaction. A neutron source is used to initiate the fission process at the precise moment for detonation. Fusion bombs incorporate a fission bomb as a trigger to generate the extreme temperatures and pressures required for fusion to occur. A secondary stage containing fusion fuel, typically lithium deuteride, is surrounded by a tamper made of a dense material like uranium. The fission explosion compresses and heats the fusion fuel, igniting the fusion reaction and amplifying the overall explosive power. The heart of a nuclear explosion lies in the concept of a chain reaction. In a fission bomb, the process begins with a single neutron striking the nucleus of a fissile atom, such as uranium-235. This impact splits the atom, releasing a tremendous amount of energy and, crucially, additional neutrons. These newly released neutrons then collide with other uranium nuclei, causing them to split as well, releasing even more neutrons and energy. This cascade of fission events, each releasing energy and more neutrons to propagate the process, constitutes the chain reaction. The reaction unfolds with incredible speed, liberating a colossal amount of energy in a fraction of a second. The energy released manifests as an intense burst of heat, light, and radiation, creating the characteristic blinding flash and devastating shockwave of a nuclear explosion. The efficiency of the chain reaction depends on the purity and configuration of the fissile material. Highly enriched uranium or plutonium, meaning a higher concentration of fissile isotopes, increases the likelihood of neutrons striking and splitting atomic nuclei. The shape and density of the fissile material are also carefully designed to maximize the number of neutrons interacting with nuclei and sustain the chain reaction. In a fusion bomb, the fission reaction serves as the initial spark that ignites the fusion process. The intense heat and pressure generated by the fission explosion compress and heat the fusion fuel, typically lithium deuteride. This extreme environment forces the light atomic nuclei within the fuel to overcome their natural repulsion and fuse together, releasing even more energy than the fission reaction that initiated the process. The detonation of a nuclear weapon unfolds in a series of distinct stages, each characterized by specific physical phenomena and devastating consequences. The initial stage, lasting only a fraction of a second, is the blinding flash of light and heat. This intense burst of energy, radiating outward at the speed of light, vaporizes everything in its immediate vicinity and creates a fireball of incandescent plasma. The second stage is the blast wave, a wall of highly compressed air that expands outward from the explosion site at supersonic speeds. This shockwave obliterates structures, levels buildings, and creates hurricane-force winds that can extend for miles. The blast wave is responsible for a significant portion of the physical damage caused by a nuclear explosion. As the fireball cools, it rises into the atmosphere, creating a massive mushroom-shaped cloud. This cloud, laden with radioactive debris from the explosion, is the source of the infamous nuclear fallout. Fallout consists of a mixture of radioactive isotopes, many with long half-lives, meaning they remain dangerous for extended periods. The fallout descends back to Earth, contaminating the environment and posing a long-term threat to human health. Exposure to high levels of radiation can cause acute radiation sickness, leading to a range of debilitating symptoms and potentially death. Long-term exposure to lower levels of radiation can increase the risk of cancers and other health problems. One of the most insidious aspects of nuclear weapons is the lingering threat posed by radioactive fallout. Unlike the immediate devastation caused by the blast and thermal radiation, the effects of fallout can persist for decades, contaminating the environment and posing a long-term threat to human health. Understanding the nature of fallout and its impact is crucial to grasping the full scope of nuclear weapons' destructive potential. Fallout consists of a complex mixture of radioactive isotopes created during the nuclear explosion. These isotopes, ranging from short-lived to long-lived, emit various types of radiation as they decay, posing different levels of risk to living organisms. Alpha particles, beta particles, and gamma rays are the primary types of radiation emitted by fallout, each with varying penetrative power and biological effects. The distribution and intensity of fallout depend on factors such as the size and type of nuclear weapon, the altitude of the detonation, and prevailing weather patterns. Ground bursts, where the weapon detonates at or near ground level, produce the most fallout, as large amounts of soil and debris are vaporized and irradiated, creating a highly contaminated plume. Airbursts, where the weapon detonates at a higher altitude, produce less fallout, as the fireball does not interact as directly with the ground. However, airbursts can still create significant fallout, particularly if the detonation occurs at a low enough altitude to draw in large amounts of dust and debris. The impact of a nuclear explosion extends far beyond the immediate zone of devastation. The release of massive amounts of energy into the atmosphere can have profound effects on the global climate, potentially triggering a nuclear winter scenario. This hypothetical phenomenon, characterized by a significant drop in global temperatures and widespread disruption of weather patterns, arises from the injection of vast quantities of soot and dust into the upper atmosphere. The soot and dust, lifted into the stratosphere by the powerful updraft of the nuclear explosion, can block sunlight from reaching the Earth's surface, leading to a cooling effect. The resulting drop in temperatures, combined with disruptions to precipitation patterns, could have devastating consequences for agriculture, ecosystems, and human societies worldwide. The long-term environmental consequences of nuclear explosions are not limited to climate change. Radioactive fallout can contaminate soil, water, and air, rendering vast areas uninhabitable for extended periods. The biological effects of radiation exposure, including cancers, genetic mutations, and birth defects, can persist for generations, casting a long shadow over the affected populations. The use of nuclear weapons, even in a limited conflict, could have catastrophic consequences for the global economy and international security. The disruption of trade, travel, and communication networks, coupled with the widespread fear and uncertainty generated by a nuclear event, could trigger economic collapse and political instability on a global scale. The advent of nuclear weapons has forced humanity to confront a profound moral dilemma, wrestling with the ethics of possessing and potentially using weapons capable of such unimaginable destruction. The sheer scale of death and suffering that these weapons can inflict, coupled with the long-term consequences of radiation and environmental contamination, has led many to question the very legitimacy of their existence. The indiscriminate nature of nuclear weapons, their capacity to kill vast numbers of civilians and combatants alike, raises fundamental questions about the principles of proportionality and discrimination in warfare. The use of these weapons, even in a limited conflict, could result in a level of death and destruction that far exceeds any conceivable military objective, blurring the lines between legitimate military action and outright genocide. The long-term consequences of nuclear weapons, including the risk of accidental detonation, the proliferation of nuclear materials, and the potential for escalation to a full-scale nuclear war, add further layers of complexity to the ethical debate. The mere possession of these weapons, even if never used, creates a constant state of existential threat, casting a long shadow over international relations and the future of humanity. The development and use of nuclear weapons have also raised concerns about the role of scientists and engineers in the creation of technologies with such destructive potential. The ethical responsibility of individuals working on these projects, the balance between scientific curiosity and the potential consequences of their discoveries has been a subject of intense debate and soul-searching within the scientific community. The future of nuclear weapons remains uncertain, caught between the opposing forces of disarmament and deterrence. The ideal of a world free from these devastating weapons, a world where the threat of nuclear annihilation is relegated to the history books, continues to motivate disarmament advocates and inspire international efforts to reduce nuclear arsenals. The concept of nuclear deterrence, the idea that the possession of nuclear weapons by multiple states prevents their use through the fear of mutually assured destruction, has been a cornerstone of international security for decades. Proponents of deterrence argue that the threat of nuclear retaliation serves as a powerful disincentive against aggression, maintaining a precarious balance of power and preventing large-scale conflicts. However, the effectiveness and long-term sustainability of nuclear deterrence are increasingly questioned. The proliferation of nuclear weapons, the emergence of new nuclear-armed states, and the potential for accidental or unauthorized use all contribute to a heightened sense of risk and undermine the stability of the deterrence paradigm. Technological advancements, such as the development of hypersonic missiles and sophisticated cyber warfare capabilities, further challenge the traditional assumptions of nuclear deterrence. The increasing speed and unpredictability of modern warfare, coupled with the vulnerability of command and control systems to cyber attacks, raise concerns about the potential for miscalculation and escalation to nuclear conflict. The nuclear age, ushered in by the blinding flash over Hiroshima, has presented humanity with a profound and enduring dilemma. The power of the atom, unleashed in its most destructive form, has cast a long shadow over international relations, the fate of the planet, and the very essence of our humanity. The quest for a world free from the threat of nuclear annihilation remains a defining challenge of our time. The legacy of nuclear weapons is a complex tapestry woven from scientific ingenuity, political ambition, military strategy, and moral reckoning. The horrifying consequences of their use, the specter of radioactive fallout, and the enduring threat of accidental or intentional detonation serve as stark reminders of the stakes involved in this existential equation. The path forward, navigating the treacherous terrain between disarmament and deterrence, demands a delicate balance of realism and idealism, pragmatism and principle. The pursuit of a world free from the threat of nuclear war requires ongoing dialogue, international cooperation, and a commitment to finding peaceful resolutions to conflict. The nuclear dilemma is not merely a matter of international diplomacy or military strategy. It is a fundamental question about the nature of our humanity. The choice we face, whether to wield the power of the atom for destruction or harness it for the betterment of humankind, will shape the course of history for generations to come.